Hello students. Welcome to week 7. One more week for this class. I just spent 45 minutes recording this class, but I just realized that my microphone was off, so I'm going to record this again. So if I'm mixing my words, please bear with me, but this is the second trial of this recording. All right, so again, this is week 7. I changed the syllabus. There were some errors which I just modified to capture what we're going to be covering this week. We're going to be covering sections 7.1 to 7.3, in chapter 7, 7.1 to 7.5 of chapter 7. And then we're also going to be covering 8.1 to 8.5 of chapter 8. Okay, so let me just try to open this here. I'm always confused with this Blackboard thing here, but just give me a second here. Okay. Yes, so I made some slight changes here. Okay, so we're going to be covering week 7 I/O and operating systems, and the required reading is 7.1 to 7.5 for chapter 7 and 8.1 to 8.5 of chapter 8. And I made some modifications to your homework as well. I'm asking you folks to do 8 simple exercises. You'll notice that these are, the earlier exercises of these chapters. Intentionally, these are easy. I don't expect these questions to take you folks more than 1, maximum 2 hours to complete these ones. Why? Because this is the week that your projects are due. Okay, folks, please do not wait for the last minute to complete your projects. Start those projects now, or you should have started them last week. But please do not wait for the last minute. Do not procrastinate. These are simple exercises. Please make sure that you dedicate the time to complete them. Okay? Okay, having said that, let's do this. So chapter 7, we're going to be learning 7.1 to 7.5. That's all we're going to do. We're going to be learning about input-output systems. Input, how the computer gets data in, and output, how the computer spits data out. Okay, so we're going to be learning about that. So the objectives is to understand I/O systems. I/O methods and architectures become familiar. We will not do storage devices though, so we're going to skip that because again, we're short on time of the course. It says all computers have I/O devices, right? You talk about your keyboard, you talk about your mouse, you talk about your monitor. This is I/O. Your camera is I/O, your speaker, your microphone is I/O. So these are the things that we call them peripherals, how the computer gets information into it. And your monitor or your speaker are output systems because this is how the computer outputs information from it. Okay, so this is I/O. One of the things you folks would be learning in your journey of computer science is that generally there's what they call CPU-bounded processes. That's where the computer spends most of its time. When a process spends most of its time on the CPU, and then you learn of I/O-bound processes where the process spends most of its time performing I/O, talking to the network drivers, talking to the keyboard, right? So here we're saying that if you have the fastest CPU in the world, yet your I/O driver is slow, the computer is going to appear sluggish. If your processor is fast, but your monitor is slow, or your keyboard is slow, or your mouse is slow, the system will just appear sluggish, right? So that's what it's saying here, okay? So we'll keep going. So this Amdahl's law is one of the most important concepts that I'd like you folks to grab from this chapter. Amdahl's law. Amdahl's law is a way to quantify system performance. So the overall performance of a system, it says, is a result of the interaction of all of its components. System performance is most effectively improved when the performance of one of the most heavily used components is improved. That's what Amdahl is saying, right? So the idea is quantified by Amdahl. He says S, where S is the overall speed up, F, so S is equal to 1 divided by 1 minus F plus F divided by K, where S is the overall speed up, F is the fraction of work performed by a faster component, and K is the speed up of the faster component. Again, S equal to 1 divided by 1 minus F plus F divided by K. That's Amdahl. So this is very important. So let's look at a slide here. So it says Amdahl's law gives us a handy way to estimate the performance improvement we can expect when we upgrade a system component. Okay, so let's look at this example. Let's say on a large system, suppose we can upgrade a CPU to make it 50% faster by spending $10,000. Or we can upgrade a disk for $7,000 to make it 150% faster. So you have two choices. You can either update the CPU to make it 50% faster for 10 grand, or you can update your disk to make it 150% faster for $7,000. Now, for this machine, processes that run on this machine spend 70% of your time on the CPU. So we call these processes would mostly be CPU bound, while they spend just 30% of their time waiting for disk. So if you have such a system, would you rather upgrade your CPU or would you rather upgrade your disk? Right, that's where Amdahl comes in. So Amdahl says F, remember, S is equal to 1 divided by 1 minus F plus F divided by K. Right? So if you plug in the numbers, F is 50. Well, let's think about this again. F is the fraction of work performed by the faster component, and then K is the speed up. So if 70% is the percentage of time spent on the CPU, then F for the CPU is 0.7. Does that make sense? So in this first block here, we're trying to calculate the speed up if we decided to upgrade the CPU instead. So F is going to be 0.7 for the CPU, and K is equal to 1.5. Why is K 1.5? A 50% increase is equivalent to 1.5. Okay, why? Because 50% is equal to 0.5, right? This is 0.5. Therefore, 50% increase over existing performance is going to reflect that's 1 plus 0.5, which is 1.5. Okay, similarly, 150% increase. Let me do this again. Similarly, if you say 150% increase over existing speed, you know 150% is 1.5. Therefore, 150% increase over existing speed will be reflected as 1 plus 1.5, which is 2.5. Okay? Let's do another one. 350% increase will be reflected as 3.5. Therefore, a 350% increase over existing speed will be reflected as 1 plus 3.5, which is equal to 4.5. And this becomes your K factor. Okay? So if you go back here, F, which is the percentage of time the CPU spends in that process, is 0.7. K is the speed up, that's 1.5. So if you plug in the numbers into the formula, you would see that S is 1.3. Okay? If you do similarly for the disk, you would say that S is 1.2. Okay? So based on this, which one would you decide to spend your money? Would you decide to spend your money upgrading the CPU? Or would you decide to spend your money upgrading your disk? So I'll leave you folks to decide this. read it, read the Amdahl's law, see what he's recommending, and then use this example to determine which of these components would you rather upgrade. Okay. All right. So that is that. Now, we talked about Amdahl. Amdahl just told us how to, what part of the system do we want to upgrade. However, there is, the whole concept of I/O subsystems, right? You have the input and the output. So there is a subsystem on the machine that is responsible for grabbing input from the peripheral devices and for pushing data to the peripheral devices. There is also a component of the computer that's responsible for deciding, to serve interrupts, to control the data that's flowing across those buses. You call them the buses, the lines that move data into and out of the system. Okay, all of this comprises of the I/O subsystems. Okay, so here's an example. Here we have the CPU. You have main memory. The CPU communicates with the main memory through the bus, as you see that. You also have these I/O modules. The I/O modules are those things that are responsible for communicating with the device drivers. These things are called device drivers. These are the things that interface with those external devices. Okay, so a device driver right here, it interfaces with your monitor and keyboard. So the I/O bus is what is used to communicate data to the I/O modules, and then the I/O modules now interface with the device drivers. The device drivers now interface with the peripherals. Okay, so all of this stuff is now resident on the motherboard. So all of this, the I/O modules, the device drivers, the buses, all of these things in totality is what we call the I/O submodule. All right, so how does the computer, the CPU, get data from these I/O devices? How does it do that? That is what we call, I/O architect. Well, one of the ways, that's what we call the strategies that the CPU uses. I'm trying to find a word that's used to encapsulate all of the strategies. I cannot find it now. But there's several ways. Right, I/O can be controlled in 5 general ways. The first one is programmed I/O. Programmed I/O reserves a register for each I/O device. So for your keyboard, for your mouse, for your monitor, there is a register that's reserved for each of these devices, and the CPU polls for this data frequently. Let me grab my textbook. Just a moment, please. So the CPU polls for data periodically by reading the data of those registers. So that's what we call polling. So that's programmed I/O. Okay. As you can imagine, this is very ineffective. It's very ineffective. Polling strategies generally are very ineffective, right? Because the CPU is spending time, because the CPU may go to the registers and there's no data there for it yet. Okay, so programmed I/O is very ineffective. The next one is interrupt driven. So interrupt driven is where the CPU is just busy executing its logic and then it receives an interrupt. We learned about interrupts in the previous chapter, right? The CPU is executing its logic and it gets interrupted. You say, hey CPU, there's some data over here. Go read the data. And as you can imagine, interrupt driven I/O is more efficient because the CPU will not go to get data. It will not go to these areas to get I/O data. It would only go when there is data and it was signaled by an interrupt. Okay. Memory mapped. What is memory mapped? So memory mapped I/O is when there's a memory address space that is reserved for both I/O devices and program memory. In other words, you have a block of memory that is shared by both the I/O devices and program memory. That's memory mapped I/O. Direct memory access, where we offload all I/O processing to a very special purpose chip that takes care of all the details. And then channel I/O, use dedicated I/O processors. Okay, so this is all covered between section pages 417 418 all the way to, no, I think pages 417 and 418 to cover all of this all the way to 419. Okay, so straightforward reading. I don't expect any challenges here. Again, if you folks are reading through this and you need some clarifications, please let me know. Okay. All right, so let's talk about, let's see what, this is a diagram that explains interrupt-driven I/O. So you have the interrupt controller here, you have the CPU, you have this INT as the interrupt line. This is how the CPU is signaled that it has to serve as an interrupt. And this DO and D1 would be data lines. But as you can imagine, when you type on your keyboard, keyboards are generally interrupt-driven. Keyboards, mouse, disk, right? Remember, interrupt-driven I/O is more efficient than polled or programmed I/O, right? So as you type on the keyboard, an interrupt is sent each time you type on the keyboard for the CPU to act upon that and to retrieve that data or the character that you typed, okay? All right. So we talked about interrupts. We learned that in the previous chapter. And this image just really talks about an interrupt, how it works. So when the computer starts, let's say that an interrupt signal is detected by the CPU. It saves all what it's doing right now, the variables, the registers, it saves that into some special space. It goes and looks up the interrupt service routine, the address of the interrupt service routine, because it has to execute that program, that chunk of code. It places the address onto the stack, and then it branches to that. It executes that logic here. It starts executing the logic. It performs all that work. And when it's done, it returns, it restores the saved registers and the variables, and then it continues executing where it left off. Okay, so this is a diagram that really summarizes how a computer is interrupted and how it serves the interrupt on the machine. We talked about direct memory access, where you have a dedicated, where we're offloading all I/O to a very special purpose chip. This is what it says. This DMA is a very special purpose chip. Its job is really to manage I/O. So you can read through all of this and read through channel I/O. You'll read through a concept called multiplexing in there. Again, straightforward reading. I don't expect any challenges there. You read through the concept of this is how a bus connects to a disk drive, and you're reading in sections 7.5. It just quickly talks about data transmission modes. Again, very straightforward reading. How we talk about parallel data transmission, parallel cables, FATA and serial cables. So just read through all of this to gain a quick overview on just data transmission in general. And that should sum up chapter 7. Okay, so again, we talked about I/O, input-output, I/O subsystems that comprise of the I/O modules, the buses, the transmission lines, the devices, the peripherals, the device drivers, right? All of that comprises of the I/O subsystems. We learned about the different ways that the I/O is programmed or is managed by the CPU. We talked about programmed I/O, where you had dedicated registers mapped to I/O devices. We talked about interrupt I/O, where the CPU is interrupted and it goes and fetches for the I/O data. We talked about what's the other one? We talked about memory mapped I/O, and we talked about DMA. Again, there's a different ways that the CPU retrieves data from the I/O devices. Okay, we talked about Amdahl's law, which is a formula that allows you to be able to determine if you have to make a system upgrade and you have different choices, different options, which one would you pick? Okay, again, if there's something that you want to get out of this chapter, is that Amdahl's law, because it applies to many things in daily life, as well as the I/O mappings. I think is also very important. Okay, let's look at chapter 8. Let's see. So for chapter 8, we're going to do 8.1 to 8.5 as I mentioned in the syllabus. 8.1 to 8.5. Again, this should be very, very straightforward reading. I don't expect you folks to have any challenges within this chapter. Again, it's actually very pleasurable reading. We're going to learn about quickly operating systems. And then we will quickly talk about the Java programming language. And then that should be it. Okay, so I am going to skip through these first few slides because they really talk about the history behind operating system. I think this is stuff that you folks can read on your own. So let's skip to all of the sections here. But here there's a concept of multi-programming, which is achieved where the CPU is allocated time slots. We'll talk about this later in the chapter. There's the concept of context switching, where when the computer has to, remember, we talked about serving an interrupt, when the computer has to save all what it's doing right now to switch to something that is called context switching. All right, so multiprocessors. You all have machines that probably are running more than one processor, right? A multiprocessor machine is a machine that has more than one CPU, okay? And while it's good because it speeds things up, obviously you have two CPUs that are executing programs. One of the challenges that you have in multiprocessor machines is that somebody has to manage conflict, right? Because remember, you have one memory, one resource. Excuse me. So if you have one block of memory and you have two processors all trying to share the same memory block, remember we talked about memory mapped I/O or programmed I/O, right? If you have a dedicated block of memory that is mapped to I/O and you have multiple CPUs trying to use that same block of memory, who writes to the memory first, right? So somebody has to manage that. Excuse me. One moment, please. So somebody's got to manage that, right? So we're going to be learning about, the operating system kernel. That's that piece of logic that is responsible for doing all of these things. Now, there's another concept called tightly coupled multiprocessors. Tightly coupled multiprocessor systems share a common memory, right? So if you have two processors all sharing the same memory, who determines who writes to the memory and who does not write to the memory? Right, so these are tightly coupled multiprocessors. And then you learn of loosely coupled multiprocessors are those ones that do not share. They all have their own separate memory, right? So these ones are called distributed systems because they all have their own separate memory. Okay. Now, another type of distributed system is a network system which consists of a collection of interconnected collaborating workstations. So, for example, let's use Blackboard, right? If you have Blackboard as a software system, is leveraging, let's say, Outlook, is leveraging another application over there, and all of these software components are collectively managed by, let's say, by the Blackboard system itself. You can think of these disparate systems or these different systems as distributed systems. Okay. Now, let's talk about real-time operating systems. So you will learn of real-time operating. You hear of the term real-time operating systems. Some of you probably have heard of this term. There's hard real-time operating systems. Real-time operating systems are systems that have very, very tight timing constraints. Very, very tight timing constraints. If you think about an airplane, right? An airplane must have a real-time operating system because it has very, very tight timing constraints. Things cannot go wrong. If you think about, let's say, air traffic controllers. If you think about nuclear reactors. If you think about spaceships. If you think about anything that, there's very, very hard timing constraints. These kinds of tasks must be executed by real-time operating systems. Okay, and then the soft real-time operating systems do not necessarily need to have timing constraints. So let's say QNX is an example of a real-time operating system. You folks can do research. What type of operating system is run on airlines, on an airplane? like the Airbus or the Boeing airplane. What is the predominant operating system that is used to run airplanes? And you would see that these are generally real-time operating systems. Now, so that's for real-time operating systems. What about personal computers? I'm on a Mac. Some of you folks are on Windows. So these are personal operating systems, and these ones are generally designed for ease of use, not high performance, and therefore these ones are not classified as real-time operating systems. Okay. And what is this? The idea that revolutionized small computer operating systems was the BIOS. And that was a chip that permitted a single operating system to function on a different type of small systems. So this thing takes care of the details involved in addressing divergent peripheral device designs and protocols. So I'll let you folks read through this. It should be straightforward reading. I don't expect you folks to have any challenges understanding the concepts here. But if you do, please, again, feel free to reach out to me and let me know. So let's skip through this history and let's talk about the operating system kernel. You folks must have heard of this operating system kernel. It is that bit of code, one of the most important bits of code in a computer. So the kernel is the thing that is almost represents the operating system. The kernel is a thing that performs scheduling. The kernel is a thing that performs memory synchronization. The kernel is a thing that does memory management, interrupt handling. So the kernel is the thing that provides all of the services of an operating system. Okay? Security, protection, interrupt handling, I talked about that. Right? So that is the kernel. Now, there are two types. There's the microkernel, which provides minimal functionality with most services carried out by external programs. And then you have the monolithic systems that provide most of the services within a single operating system. So microkernel would be really, let's say, stuff like Unix. This is typically, I think this would be a real-time operating system. That would be a microkernel. And stuff like Linux, Mac OS, DOS, these ones are monolithic kernels, right? And then, you think about iOS, that'll be monolithic as well. Android as well will be monolithic. And these ones are not hard real-time operating systems. All right, so I skipped through this. We talked about the kernel managing all of these system activities. Let's talk about scheduling. How does an operating system, on your machine, you have, let's say, 50 programs, right? In your Chrome browser, you have, let's say, 50 tabs open. How does the operating system know which program to execute? Right now I'm probably running 10 programs at the same time. So this is where scheduling comes in, right? The operating system schedules work. So there's several ways. There's long-term scheduling, there's short-term scheduling. I'll let you folks read through this. But what I want to cover here is, let's see, yes, this one. Right, so there's 4 approaches to scheduling. First come, first serve, where the first job that comes into a queue is what is serviced first. Okay, there is that. Another one is the shortest job. So the shortest job that the CPU has to perform is the one that is done first. But the challenge is, how does the CPU know how long a job is going to take? So this one is hard. Another scheduling approach is round robin. Round robin is where you have an allocated time for each job. Let's say you have the CPU allocates, let's say, 100 milliseconds to do each job. Let's say you have 50 things running on your machine. The CPU would allocate 100 milliseconds for each of those things. An example, analogy. Let's say that you're taking 4 classes. If you dedicate 1 hour for each of those classes every day, right? 1 hour for gym, 1 hour for CS, 1 hour for economics, 1 hour for biology, and you go back again. That is round robin because you're just dedicating 1 hour for each of those things. And as you can imagine, context switching is very heavy here. Okay. And then priority is where a job is scheduled based on its priority. Again, one of the challenges here is that how does the CPU determine which job is more important than which one. Okay, so these are the four approaches that a CPU uses to kind of schedule jobs that it has to execute upon on the machine. Okay, so that I'll let you folks read through that section. I'll let you read through protected environments. Nothing that I need to explain here. This is all straightforward stuff. Subsystems, we talked about that. For logical separation of your machines, so it provides the security and protection. Nothing for me to explain here. You folks can read through all of this stuff. And let's see. But we will talk about, before I let you folks go, I will just quickly talk about programming tools, and I'll end this chapter with the Java programming language. So what are programming tools? What are programming tools, folks? Some of you have experience with Java, Python, C++, C. Programming tools carry out the mechanics of software creation within the confines of an operating system, right? In other words, we software engineers, we write code using programming tools. And when we write code to execute on your machine, the code that you write has to be compiled first to what is called, in some cases, if you're writing C or C++, that code is compiled directly to assembly language and executed on a machine. If you write code using, let's say, Java, C#, and I think, those two, that code is not compiled directly to binary. That code is compiled to what we call bytecode. And then the virtual machines in this environments, whether it be the JVM or the .NET CLR, those environments now then take the bytecode and translate that into assembly language, and it's that code that is executed on the machine. Okay, so that's kind of very, very high level, 30-second summary of what programming tools is all about. So I'll let you folks read through this. Again, the output of most assembler is a stream of relocatable binary code. That is what is stored on the machine, and that is what is executed by the CPU. We learned about assembly code in the previous chapter. I don't need to talk about that. The process of assigning physical address to program variables called binding. We talked about that. One of the assignments in the previous chapter was actually creating this. What did I call it again? The variable table. Okay, so that's kind of concept of binding. How do you map a physical address to a program variable? Okay. So read through all of this. Dynamic linking is when, there was a concept of linking before, where you take a program, you link it based on the operating system. That's all dynamic linking. Read through all of this. Again, it should be straightforward stuff. If there's any questions, please feel free to let me know. This pyramid just talks about ease of human understanding. We certainly don't understand binary code. That's for the computer. Also, we can read assembly, but again, you prefer not to write code in assembly. It takes a long time. And then Java, C++, Fortran is the third generation of programming languages. SQL is the fourth, and then now we're talking about natural language processing today. All right, so let me end this chapter with just talking about, again, Java. One of the most popular programming languages out there. And why was it popular? Because Java was built to run on different operating systems. And how does Java do that? C# is the same today. C#.NET can run on different operating systems. And how did they do this? Java and C#, they have this system called the Java Virtual Machine for Java, and for C#, Microsoft is called the .NET CLR. These are systems or software that runs on the machine. So you have a JVM for Windows, you have a JVM for Mac, You have a JVM for Linux. And similarly, you have a .NET CLR for Windows, for Mac, and for Linux. And what happens is that these things allow the language to run on any platform for which the virtual machine has been written for. Okay, now Java is both a compiled and an interpreted language. Why? Because when you write Java or C# and you compile it using the Java compiler, the output of that process is what we call the bytecode, right? So the computer does not execute bytecode. The Java virtual machine, once you run the program, the Java virtual machine takes the bytecode that was compiled from the Java compiler. It now converts that bytecode to assembly language, and that is what is executed by the CPU. Here's an example. So you write your program in IntelliJ, whatever IDE you use, you compile that. It creates this .class files. And then once you start to execute, again, this is all happening during runtime. So this left two boxes is what we call compile time, and this box is what we call runtime. So once you start to execute the program, the JVM takes the bytecode, it loads it in, it interprets it, it converts it to assembly language, and that is what is executed by the CPU. Okay, so at execution time, the JVM must be running on the host machine. It loads and executes the bytecode class file. It verifies the integrity of the bytecode, and then it performs a number of runtime checks, and then it does the magic to interpret that, convert that to assembly. So that's it, folks. That's it. That's a short chapter. A very nice short chapter. We just talked about operating systems. We talked about the kernel being the main component of the operating system. It does the synchronization, memory handling, interrupt servicing, context switching. That kernel is the most important thing. We talked about real-time operating systems, hard real-time operating systems, and those are the operating systems that have very tight timing constraints. For example, the operating system that runs airplanes. You guys should check that out. We talked about soft real-time operating systems. These are operating systems that necessarily don't have hard timing constraints. We talked about the Windows and Mac. We talked about monolithic and microkernel, monolithic kernels and microkernels. We talked about those, and we then ended up talking about the Java virtual machine, right? So light reading. Again, I don't expect you folks to have any challenges within this chapter. If you do, please, there's so much out there that you folks can research on your own. Reach out to me if you have any questions. But again, I don't expect you folks to have any questions or any challenges with this chapter. So before I end, please, again, I repeat, your assignment is due. Very easy questions I give you folks this week. Please prioritize your assignment. Your project is also due this week. Please prioritize that. Prioritize your project. And, I am thinking I may spend some time to cover some sections or some topics prior to the final exam. Final exam, expect it to be maybe 20 questions across all those chapters. We may, bias a little bit towards the last chapters, but again, just think about the final exam as another assignment. Again, if I'll be expecting you guys to don't procrastinate, take your time, start early, and especially with your project, please, don't procrastinate. Start the project early and send it in to me because I need to mark these things before I submit your final marks. Okay. So again, if you have any questions, please reach out to me. But again, the assignment that I have provided for you folks this week should be easy. It should not take you more than 2 hours if you sit down to get them all done. Okay? Good luck, all the best, and reach out to me if you have any questions. Thank you.